worked on related topics, but more in connection with cosmology, it's matter-physics, and that would probably not fit the subject matter of the meeting. Of course, I thank the organizers for having invited me to attend, and so let's see what this is about. Acknowledgements. When I started to be interested in the quantum Hall effect, which was in the around 86, 87, I profited a lot from discussions with the late Rudolf Mock, who was a great expert in this area. And then I had a chance of encountering many very talented young people, for example this one, and so on, who worked with me on various aspects of this story. And so in the end we had quite a number of papers. And among people who, pretend to be important physicists, there was essentially nobody who appreciated this work, but Paul Wiegmann always said it was interesting, so that was very encouraging. All right, so here is a table of matters. So I will briefly recall what effective actions and chiral anomaly are about. Then I will apply this to the edge current and the bulk transport equations of the Hall effect. And then I will also briefly talk about spin currents in planar topological insulators with time reversal invariance. I think that's sufficiently closely related to the topics of this meeting for me to say a few words about it. Very good. So here is a summary. I will describe the goals of my analysis and survey the chiral anomaly. I will then review some basic elements of the theory of the quantum Hall effect in two-dimensional incompressible electron classes. I will discuss the role of the anomalous chiral edge currents and the anomaly inflow from the bulk. And of course this applies to all insulators, but also to Chern insulators. Almost the same story at some level of generality. And then I will look at these 2D topological insulators with time reversal invariance and with edge spin currents. And I may mention a few open problems or things like that towards the end. If you want to read up with a few details about this story, thanks to Michele Graf, I had to write a review paper for a special volume of the Journal of Mathematical Physics. So there you find a sort of summary of my point of view and my results with relatively few technical details, so I think it's very readable. Good. So let's get started. So I consider an insulator that consists of a two-dimensional electron gas in a neutralizing ionic background. The electrons are confined to some region of the plane. You should think of the plane as being an interface between a semiconductor and an insulator, and you turn on a gate voltage that pushes the electrons towards the interface. And there they form a very nearly two-dimensional gas of electrons. Then the whole thing, in the case of the Hall insulator, the whole arrangement is put into a homogeneous external magnetic field transversal to this interface. So then I want to consider the response of the system if I modulate the external electric magnetic field by small amounts, just like in Abanov's talk yesterday. I describe my external electromagnetic field in terms of the vector potential A, which is a 1 pushing the right button. So this is one form which describes the external electromagnetic field. If the longitudinal conductance vanishes, meaning that the gas is in an insulating state, then it is easy to guess the form of the effective action. What is the effective action? Let's suppose the gas at very, very low temperature, essentially at absolute zero. And then I compute the functional integral, the evolution of the ground state when you turn on a small perturbing external electromagnetic field. And in the end, after a long time, suppose you are in the ground state again. That is the partition function. I call this the partition function. Now I compute the logarithm of this partition function. I multiply by minus IH bar. This was in fact missing. That's why I had to upload the minus IH bar was missing. So it would have been a terrible mistake. And so you can guess the form of this. Since the gas is in an insulating state, this effective action should probably be a local functional of vector potential and its derivatives, and you should impose gauge invariance, because in quantum mechanics you never break the gauge invariance. And so you can order the terms arising by their scaling dimension. The most relevant term in 2 dimensions, assuming that parity and time reversal are broken, is the Chern-Simons term. That's this term. Then the second most relevant term is the Maxwell term. Epsilon on dielectric is the tensor of dielectric constants, and mu is the magnetic permeability of the insulator. Now, as I said, you should impose gauge invariance. Now, if the sample has a boundary, then unfortunately the Chern-Simons term is not gauge invariant, because if you gauge transform the vector potential, you get the boundary term. The proportional linear in the gauge in the generator of the gauge transformation. And so this anomaly should be cancelled by a boundary term in the effective action. All right. So what is this boundary term? So here I just do the computation which I just summarized in words. The boundary term that cancels this anomalous term here, proportional chi. Chi generates the gauge transformation. Well, this boundary term is called the anomalous chiral effective action. It is easiest to write it down by introducing light cone coordinates. The velocity of light, the role of the velocity of light is played by propagation speed, speeds of tension modes. In fact, the correct boundary term is a sum of terms like that may differ from one another by having different propagation speeds. I neglect this little complication. All right, so that's the boundary action. And, it's now an exercise maybe for you to check that if you gauge transform this chiral boundary action, you just get the same anomaly as from the Chern-Simons theorem.
So just a question.
You have already a question. If you ask too many questions, I will turn you off, but you can now ask one question.
How is the effect of the electrostatic potential modeled here? Is there a way to model the effect of the potential, the confining potential, from the Chern-Simons perspective?
No, you mean the edge potential?
For example, yeah.
No, does it appear here?
Exactly.
I'm looking at the effective action in the scaling limit. Very large distance scales, very low frequencies. You don't see all the edge potentials do the same thing. You see, the edge becomes infinitely narrow in the scaling limit.
But the velocity of edge modes should be sensitive to the gradient of the potential.
Of course. But they are just parameters here.
Right. So it's
I do not compute them, and now that's the end of the question. Okay. All right. tell the story from a different point of view. I have an insulator, but of course, even in an insulating state, there are operators describing currents, the conserved currents of the system. In 2+1 dimensions, a conserved current has a vector potential. If you look at the two-form dual to the conserved current, it is the exterior derivative of a vector potential, which I denote by B. And then you can say, well, if J is the dual of the, say, electromagnetic current of the insulating state, what is the action that describes the quantum theory of this vector potential B? And again, you organize it according to scaling dimensions. And the most relevant term in this action functional is the Chern-Simons term in B. And then, of course, you have to couple the current to the external electromagnetic vector potential, and that's given by this term A, which dB. Very much like in the talk of yes?
If I may use my one question.
No, not everybody has one question. I mean, otherwise we'll never
so this mapping from the current to B is not really local, so why would the action be local in B?
What do you mean it's not local?
But if you change the current in one point...
So you just ask...
B will change not just in one point.
Yeah, that's of course...
It's not a local field.
That's correct, but you see dB is local. Okay.
dB, yes, okay, dB is...
Then you just ask, well, what kind of action functions can you have? This is an ansatz, and we will see that this ansatz reproduces, you see, for the effective action as a function of the external vector potential, the locality comes from the fact that the system is in an insulating state. So you can now ask which action for the current vector potential reproduces the right effective action. It turns out by doing a Gaussian integration, this one doesn't. Okay? So it's justified by the success of the ansatz, I would say. These are not theorems. You see, Frenchmen always have the tendency that they want to see everything in terms of theorems. But in physics, you cannot always do it. You have to check, you have to guess something, and then if it is successful, you can feel fine. All right. So that was about effective actions. We will dwell on this form of the effect of the action for the current vector potential just in a few minutes from now, if I ever get to that. So let's briefly, so this is one slide about the Chiral anomaly. So you see in all these systems of electrons, we have two types of currents, a vector current and an axial vector current that I denote by adding a little 5 underneath. And then it turns out that the axial vector current tends to be anomalous in the sense it's not conserved. So let's suppose that the fermions are massless. Then we can compute the divergence of an axial vector current, and in 1+1 dimensions, it turns out it's proportional to the electric field in the spatial direction. Okay, d mu j mu 5 equals alpha over 2 pi times the external electric field. It's also good to compute the commutator of the zero component of the axial vector current and the vector current, and in 1+1 dimensions, this commutator is proportional to the derivative of the spatial delta function. And then in 3 dimensions, there are no anomalies, but then we can pass to 4 dimensions, and then it turns out that the divergence of the axial vector current in 4 dimensions is proportional to E dot B, that's the instanton density, if you like. This one, and the commutator of the zero component of the axial vector current and the vector current is proportional to B dotted into the gradient of the spatial delta function. I'm not going to derive these formulae. There's a very nice article review article due to Roman Jacquet, who also writes less nice articles, but this is a very nice one. It's in this book about current algebra and anomalies that appeared in the Princeton University Press. So there you find arguments leading to these formulae. And we are going to exploit these formulae. Abanov mentioned the chiral magnetic effect yesterday. That's a consequence of this anomalous current commutator. It was apparently noticed first by Alyosha Vilenkin. But we didn't know that, I think, at the time. So Anton and Vadim and I sort of rediscovered it. And I think had a more general insight where it comes from. Anyway, that's as much as I want to say about the chiral anomaly. Let's go on. Let's now look at edge currents in planar insulators. That leads immediately to more or less the theory of the quantized Hall effect. The pictures here are the sort of heroes of the Hall effect from Klitzing, Stürmer, Zui, and Laughlin. Von Klitzing got a Nobel Prize for one page in a lab book, and that's this page. That's how he got this Nobel Prize. So here is the setup. You have this interface between an insulator and a semiconductor. You turn on a gate voltage and put the whole thing into a homogeneous external magnetic field. Then you perturb the electric magnetic field by a little bit of an in-plane component, E underlined, and by modulating the transversal magnetic field in the direction perpendicular to the interface by a little fluctuation. Then you derive this B and E underlined from a vector potential, and the 2 plus 1 dimensional field tensor is noted here. Okay, now we can sort of rederive the form of the effective action of a Hall insulator from the old laws that were used to describe the Hall effect already in the 19th century. So the first such law is Hall's law. It says that the current in the 2-dimensional sample is perpendicular to the in-plane components of the electric field with a constant of proportionality that is a conductivity. It's called the Hall conductivity. This law immediately, of course, says that reflections in line and time reversal are broken symmetries. And that's not so astonishing because of the external magnetic field. Your face expressed some kind of doubts.
No, I changed my contact lenses.
Oh. So the second law is the continuity equation for charge density and current density. The third law is Faraday's induction law, and now we can combine these 3 laws and find out that the time derivative of charge density equals sigma h times the time derivative of the external magnetic field in the transversal direction. It is important that this fundamental law, well, 1 is not the fundamental law, it's a phenomenological law, but 2 and 3 are fundamental laws. These 3 laws imply something about time derivatives. Now we will integrate law number 4. And when you integrate such a law, you have to pick integration constants. And so what you get is that if you choose the right integration constants, you find that the perturbation in the charge density is sigma h times the perturbation in B. I should have written here delta J naught equals sigma h delta B, because it's an increment that you get by integrating a time-dependent quantity over time, from an initial to a final time. This is related to what Eugene said about Bayer, Yang, and so on. So it's actually sort of important to realize that. Now you can combine Hall's law and this so-called Chern-Simons Gauss law. And you find a generally covariant relation between the field tensor of the electromagnetic field and the vector current density, which is this equation number 6. All right. Now I take a divergence of equation 6, then I get on the left-hand side 0 because the current is conserved. And on the right-hand side, if sigma h makes jumps, for example, at the boundary of the sample, I get something non-zero. This is puzzling because it looks like a contradiction. How do we resolve the contradiction? Well, J mu, as it appears in equation 6, is not the total current, it is just the bulk current. But wherever sigma h jumps, there could be an edge current. And in order to save current conservation, I have to assume that there are edge currents wherever the value of the Hall conductivity jumps. All right, that's how this contradiction 7 is resolved. And by themselves, neither the bulk current is conserved nor the edge current is conserved. All right. So the edge current has a support wherever the gradient of sigma h is supported, and it flows and it is perpendicular to the gradient along the edge. It flows along the edge. And so from the previous equation, the right-hand side of 7, I find out that the divergence of the edge current equals minus the divergence of the bulk current, which is minus sigma h times the electric field along the component along the edge. Well, this is exactly the equation of the chiral anomaly in 1 + 1 dimension. So apparently we conclude that edge currents have a chiral contribution that is anomalous. All right, and the anomaly of the edge current, of course, is cancelled by the divergence of the bulk current. Okay, that's the anomaly inflow. Now, since people were wondering about edge potentials, I have a few remarks here about how the gradient of the edge potential cancels the Lorentz force, and from that you can calculate the propagation speed of the edge modes and so on. This is basically classical physics. I won't go into it. Because of what we heard yesterday about hydrodynamics and anomalies and so on, it's sort of a nice observation that if you trade the external magnetic field by the angular velocity or the curl, the vorticity of a velocity field that transforms the whole system into motion, and if you replace the Lorentz force by the Coriolis force and the edge potential either by a low pressure system in the atmosphere or by the coastline, if you look at water waves along the west coast of North America, then you get again a Hall effect. You may know that when you go to the Limatour Beach in California, and then if you're lucky you see these enormous waves that travel upwards. These are edge modes of water waves whose description comes about by just repeating these arguments. And of course the same remark applies to the theory of hurricanes. You immediately make to understand why all the hurricanes in the northern hemisphere turn the same way, namely counterclockwise. Now, by going back to the chiral anomaly, you find a formula for the Hall conductivity. The Hall conductivity is given by E squared over H times the sum of the squares of the fractional charges of the quasi-particles that move around the edge. It's actually not quite the charges of the quasi-particles, but the charge numbers that show how these edge currents couple to the electric field. So that's a formula for the Hall conductivity that we get simply by recalling the theory of the chiral anomaly. That's a nice formula. And of course, you know, this whole business of edge currents, chiral edge currents, was anticipated in a paper by Bert Alperin on the basis of relatively sort of handmade quantum mechanical calculations, but turns out it's a very general phenomenon. All right. Now, there is another way of understanding why the effective action of the Hall insulator has to be given by the Chern-Simons action, and that goes as follows. Let's be somewhere in the middle of the bulk of the sample, and let's compute the bulk current. The bulk current is the expectation of the vector current density in the state of the system, and then by general nonsense, this is the same as the variational derivative of the effective action with respect to the external vector potential. And now I can use the combination of Hall's law and this, how is it called, Streda's law, and then you find that the variational derivative of the effective action is given by sigma h times the dual of the field tensor. This is the first order differential equation for the effective action, which you can easily integrate, and you find out the bulk term of the effective action has to be given by the Chern-Simons term with a coefficient equal to the Hall conductivity. And then by gauge invariance, you again find out that you have to add the boundary, the anomalous chiral boundary action. There were many discussions in the literature about the equality between the bulk Hall conductivity and the edge Hall conductivity. Here, this equality emerges directly from imposing anomaly cancellation. All right, let's go on. Well, here is the formula for the edge action. I think I already showed it before. And then a remark, what I said about Hall insulators, of course, also applies to Chern insulators. These are insulating states of electron gases without an external magnetic field, but in a background that tends to have magnetic impurities that also break the time reversal invariance. All right, so let's now ask, what can we guess or find out about the spectrum of quasi-particles in an Hall insulator? I make an ansatz for the electromagnetic current density. I say it is a linear combination of current densities that are individually conserved. This is inspired, of course, from the Landau levels of a gas of non-interacting electrons. But it's just an ansatz. I will normalize this current J alpha in a canonical way so that the coefficient Q alpha has an unambiguous meaning. Now we saw before that conserved currents in 2 dimensions have vector potentials, so I introduce vector potentials for all these conserved currents J alpha. And then, since we have to reproduce the effective action of the Hall insulator, we can guess that the action for these conserved current densities J alpha is a Chern-Simons action, and the current J alpha is given by Q alpha dB alpha, which couples to the external vector potential A. So that's in fact the complete action of the system in an external vector potential A up to terms that are less relevant, that have, higher scaling dimensions. And then again, because you see, because there is another gauge invariance, if you change the vector potential of a conserved current by a gradient, then of course this does not change the current. So again, you have to impose gauge invariance on the gauge transformations of the B's, and so that means that you have to have a suitable bandwidth. Now we can do the functional integral of e to the I times this action S lambda of all configurations of the conserved currents, and we reproduce the Chern-Simons effective action in the bulk plus the boundary action. And we get the formula for the Hall conductivity sigma h is equal to sum from 1 to capital N Q alpha squared. I have, meanwhile, I think set E squared over H equal to 1.
What is capital N?
Pardon?
What is capital N?
N was appeared in the ansatz. I just say, well, the current density J might just be a linear combination of capital N independently conserved currents. For for non-interacting electron gases, these are the current densities that refer to individual Landau levels. So that's what inspired this ansatz.
So
and
the lowest Landau level N is equal to 1?
Yes, that's right. However, when you have introduced interactions, it might be that the gap opens within the lowest Landau level, and then all of a sudden N is not 1 anymore, perhaps 2 or 3.
Can you, so for fractional quantum Hall effect, can you assign N for each plateau?
We will, no. A single plateau corresponds to a theory with several conserved current densities, as we will see. You see, it's easier to interpret what capital N means when you look at edge currents. As everybody believes, there are different species of quasi-particles circulating at the edge in a chiral fashion, and every species leads to a conserved edge current. These conserved edge currents are in 1-1 correspondence with these J alphas. But a priori, this is just an ansatz, and let's see how successful the ansatz is. And it turns out to be immensely successful, as we will see on the next slide. So, you see, you can now ask, how do we describe physical states of a Chern-Simons theory? We describe them by inserting Wilson lines or Wilson networks. If you like, maybe I should make a little drawing. Of course, I will run out of time. That's 23 already. Let's not worry. This is lambda. And then somewhere there is a cross section at constant time. I'm now asking how do I actually insert quasi-particles. But we insert them by viewing them as endpoints of Wilson lines. Perhaps we can concatenate, and maybe we need one further one to make everything invariant at this node. Now, one thing is clear. In an ordinary electron gas, there should be excitations that describe electrons and holes. Okay? Now, if this endpoint of a Wilson line describes an electron, by just adding another Wilson line of the same type, I can also describe 2 electrons, or 7 electrons, and 15 holes, and so on. What does that mean? Well, if a Wilson line is described by e to the I, some q j, I guess I called them alpha before. if this is a Wilson line that describes, an excitation of, say, n electrons, well then, by multiplying the q's by an integer, we just increase the number of electrons described by this Wilson line. This means that these q alphas, if I arrange them as a vector, these should be vertices of a module over the integers. What is a module over the integers? It's an integral lattice. So the Qs that describe multi-electron and Howell excitations in this Chern-Simons description of the insulator must belong to an integral lattice, which I denote by gamma. Okay. Now we can try to calculate the electric charge of excitations. Let's suppose I want to calculate the electric charge inside this shaded region here. How can I do it? Well, the charge operator inside this region O is given by integrating the zero component, the charge density, over O. But by Stokes, this is the same as sum alpha from 1 to capital F, Q alpha times the line integral of the vector potential B alpha along the boundary along BO. You have questions there. If you have questions and they are important, then of course I will answer them. But otherwise, you can wait for the discussions.
One question. So
Really important.
effective, well,
Go ahead.
so I'll do it. So the effective action you introduce, if I have the wave functions, is it just a norm square of the wave function? The effective action you introduced 20 minutes ago,
Yes.
you wrote it in a path integral way, but is it the same thing as a norm square of the partition function?
No, it has nothing to do
It's
with
nothing
it.
to do with it. So
Really, absolutely nothing to do with it.
how do you compute
You know,
it?
an effective action lives on space-time.
Yes.
Your wave function lives on configuration space, which is a completely different space.
So if you just have the same, you able imagine to compute the Laughlin wave function with an arbitrary
You
magnetic
cannot
field.
compute it in this formalism.
So you cannot.
You see,
compute
the
it.
Laughlin wave function was a stroke of genius, and Laughlin probably is a genius. So he guessed wave function for the ground state of this insulator. Fortunately, he made a good guess. So numerically, it appears that the Laughlin wave function is relatively close to the true wave function. It's certainly not the true wave function. You see, if you perturb the two-body interactions a little bit, your ground state wave function changes. And so, when I started to work on this, I got interested in Hall effect problems around the mid-80s. And I decided I would like to develop, it took me quite a while to get started, and that's when my discussions with Rudolf Moch were quite important. But then I decided I would like to make a theory which first of all encompasses gases with electron-electron interactions. It should not be tailor-made to non-interacting electrons. And the second thing was I wanted to do a formalism that is relatively universal, where you do not make Ansätze such as Laughlin wave functions. So these wave functions never appear in my formalism. I could say something about the sort of miraculous relationship between this formalism and ansatz wave functions, but maybe that's for the question session. All right, so we have identified the charge operator in this formalism. Okay, here it is. It's given by a linear combination of line integrals of these vector potentials B alpha. And now you see, if you compute the charge in the matrix element of the charge between two states or between the same state, to get the same state, you just reflect these open Wilson lines upstairs and put them together again. And compute this charge now, because Chern-Simons theory calculates linking numbers. You find out that the matrix elements of the charge operator in this state is nothing but, so Q, the charge inside O, expectation is nothing but some Q alpha, and then the sum of the Q alphas that are inside, whose endpoint of the Wilson lines that landing inside O. So there is a second index that indexes the Wilson lines. Let's call it I, this Wilson line I. So in particular, the charge of a single Wilson line with charge numbers little q1 up to qn is nothing but some q alpha. Okay. Now, if a Wilson line generates an open Wilson line, excites an electron, then this must be equal to 1. If it excites n electrons, it must be equal to n. If it excites n holes, it must be equal to minus. So, in other words, the vector, the row vector q1 up to qn is a linear functional on this integral lattice with values in the integers. What is a linear functional on an integral lattice with values in the integers? It's an element of the dual lattice. So this is in the dual lattice. Now, if you have an integral lattice, and then you compute, and in fact, I should say one more thing. There is a relationship between charge and statistics. If you have an excitation which describes an odd number of electrons or holes, it transforms, and you exchange it with another such excitation, it transforms like a fermion. You get the sign change. If it describes an even number of electrons or holes, then it transforms like a boson. Now, you have to know a little something about Chern-Simons theory, but that, in this mid-80s I knew these things. I still haven't completely forgotten them. Maybe I can use the other board. So, look at two pictures. Two Wilson lines like this. Is a vector q and the vector q prime, and maybe just with two q's. And now I look at the second picture where these strands have been interchanged. Like this, again a q. What happens with the state vector? You see, Chern-Simons theory is a theory which has a Hamiltonian interpretation with a Hilbert space and so on. The Hamiltonian happens to be 0 for Chern-Simons. But I can ask, how does the state vector transform? It turns out that to transit, this is twice the same state. You cannot distinguish them because the excitations are at the same positions and they have the same charge. So the state vector should be related by a phase. The phase happens to be e to the I 2 pi times q. This is the, q is just So if I have a fermion, this should be an odd integer, and if it's a boson, it should be an even integer. All right? And so, if the charge is an odd integer, it should be fermionic. If it's an even integer, it should be bosonic. So what do we have to classify to understand incompressible Hall fluids? We have to classify the following data. An integral lattice with an odd integral bosonic form given. Then a vector in the dual lattice, or point in the dual lattice, it is visible because there are sites in gamma on which Q, when you evaluate it, takes the value 1. So this is a visible vector, so called a visible vector. So you have to classify these data. And you could add a little more. You could, for example, add, if you want to know more about the edges which you will come to, you would also have to of course, you know, give this propagation speed variation. But that's maybe a little less important. So these are general algebraic data to classify, and this is a job we did. And I have to say, there is a person in the audience whose physics teacher was Emmanuel Tiron. And Emmanuel Tiron was a postdoc with me just at the moment when I started to work on this classification of Hall insulators. And he had written a PhD thesis on p-adic string theory. And now it is typical for the string theory community that it occasionally creates a hype. And p-adic strings were a hype, which of course was absurd. So by the time he had completed his PhD thesis, nobody was interested in p-adic strings anymore. But then Jean Bricmont from Louvain sent me an email message that there's this very talented student, Tiron, who has a problem finding a postdoc position because nobody wants to do p-adic strings anymore. But that he's very talented, and so I took him. And so he knew a lot, he already knew a lot about integral lattices. I had to learn it, I didn't know anything, but he already knew quite a few things. And then thanks to his presence and also thanks to some help from Louis Michel, who was also a great expert on integral lattices, we found a fairly general, comprehensive classification of this data. I will show you the results of this classification. The results, the success of the classification is quite spectacular. It comes under. Well, here is a classic. Here's the same story, but in terms of H-mode, I have to skip it because it's supposed to stop. So here's the result of the classification. We classified in detail Hall insulators with a Hall conductivity in the interval 0, 1. If it is very small, you don't get plateaus, you get the Wigner crystal. That's at least belief. Of course, there are no rigorous results, but this would be an interesting problem to show that a very dilute gas of electrons in the magnetic field forms a Wigner lattice. It's still an open problem. Like all problems about crystallization are mathematically open. Okay, then we found out that between 1/3 and 1/2, there is a totally unique series of Hall conductivities, 1/3, 2/5, 3/7, and so on. That's the so-called A series. I plot the Hall denominator vertically and horizontally the value of the Hall conductivity. This A series is related to the integer Hall effect. In fact, you get these states along the A series by what we call a shift map applied just to the Landau levels of free electrons. And then, you know, there were people like Jane with his composite fermion picture who said that the red series, which is seen here between 1/2 and 1, just arises from the A series by something like charge conjugation. This is a very stupid idea, because these plateaus along the red series can arise by charge conjugation, but many of them are not charge conjugates of anything that you find between 1/3 and 1/2. In fact, you find if you tilt the external magnetic field, then of course the coupling of the magnetic field to the spin of the electron changes. If you tilt it a lot, all of a sudden all the spins will be polarized along the magnetic field. And so you find transitions along the red series between spin polarized electron gases and spin unpolarized electron gases, which I think you don't really understand very well with the Jane picture. And anyway, apart from this charge conjugated A series, there are, you know, why do I have A, D, E? This is because an integral lattice arises always as a sublattice, which is the root lattice of the Lie algebra. A denotes the root lattices of the A series, SU2, SU3, and so on, and E of the exceptional Lie algebras, and D of the D series. And so, among the sublattices that are root lattices of all fluids along this series, you find root lattices of E and D and so on. And then, you know, something which you don't get at all in the Jane picture are these additional plateaus that are here. And our classification at least has candidates for all these observed plateaus. So that I thought was, you know, a fairly successful enterprise. It was appreciated by mathematicians. I gave a talk about these things at the International Congress of Mathematicians in '94. This is as old as this story is. It's really ancient. It's almost Archimedes. And then Vladimir Arnold wrote some kind of comments on this congress. It took place in Zurich, actually. And he thought this was a nice story, which gave me a very pleasant feeling. But I think the physicists never looked at it. I don't know why, but they didn't look at it. So that's the story about classifying Hall fluids. When you go to the edge picture, things basically repeat, except there you also have to understand the propagation speeds. You see, the bulk is topological, but the edge of a Hall fluid is dynamical. It's not a topological field theory. It's in fact something resembling chiral conformal field theories. In fact, that was the first idea. I thought one could classify the edge states in terms of current algebra. And this was a theme that was also developed. I started about this in the paper with Thomas Keller, who was a PhD student of mine at the time. And then these lattices reappear. These are, you know, current algebras with Lie based on Lie algebras of the A, D, and the E series, all of them at level 1. Now this is a classification of Hall fluids with abelian quasi-particles. Only abelian Bragg statistics appears phase factors. But at some point we decided we should also do it for possibly non-abelian quasi-particles that might appear. This was work with Pedrini, Walcher, and Schweigert, which came a little later. In fact, a few years after I had sort of worked on the general theory of Bragg statistics. which I cannot tell you anymore. In fact, I should have stopped already 5 minutes ago.
Sorry, in the picture, the fact that there is a circle around the point, it means that it is observed?
It's observed, that's exactly. Okay. Yes. Then some of them, you know, are a little bit tentative. I have to say this picture, do you know when I drew this picture? In 1994.
I know
Meanwhile, it has been translated into a text picture, which looks maybe, you know, in some sense less nice, I think.
And what is the square? What is the green square?
The squares mean that there are several different lattices producing the same Hall conductivity.
Okay.
And it's exactly for those Hall fluids where you see phase transitions when you tilt the magnetic field. So that was, you know, we felt this was a big success. All right, well, now this part obviously cannot be done anymore. Well, I think the conclusions are obvious, and this is also obvious at the moment. But I like to show this. I've shown it about 50 times already in talks. I think it shows how intelligent people sometimes can see things clearly, not just in one discipline, but also in other areas of thought. Anyway, thank you for your attention. I take further questions, although we only have 2 minutes left for the questions. The part which I could not cover is in the slides, so if you look at the slides, you will see what I would have said about time reversal invariant.
Oh, thank you for this lively account. Are there any short questions?
When this was written?
This one, 1970.
Aha. No, but
You see, it was surprisingly far-sighted. He wrote it just shortly after this meeting in Montreal,
okay.
when he was working full-time on this movement that was called Survivre et Vivre, which, you know, I find very strange that it disappeared. This movement was certainly as important as Pugwash. Pugwash still exists, it has not been a great success, unfortunately. But this one disappeared again for the reasons that I find hard to understand. So, yes. Any other short, brief question or comment? If not, then let's go. Coffee break. If I had remembered that we have the coffee break, I would have gone over time.
Maybe literature comment in hydrodynamics. You mentioned that H current of a boundary of the droplet is related, could be rephrased in terms of rotating fluid and effect of Coriolis force, which is completely right.
Yes.
So in hydrodynamics, this whole droplet is called Rankine vortex.
Huh?
Rankine vortex.
I see.
Rankine is a Scottish engineer, you can read it in Wikipedia, who first suggested that Rankine vortex is the area of an incompressible fluid where vorticity is constant and otherwise outside is irrotational fluid. Rankine vortex has an edge.
Yes.
There is mode propagating along this edge, which fully copies what you described about quantum Hall phase. There is a complete hydrodynamic analog.
Yes. Of
The only
course, the
difference-
edge can be fairly, you know, wide. As in a hurricane, the edge is very wide.
In Rankine vortex, it's edge, just edge. But a difference, perhaps, which I think is important, is hydrodynamics is non-linear story. Therefore, H propagating along this Rankine vortex also non-linear. anomaly and all this topological argument in the bulk, declaration of topology in the bulk, determine only small part of evolution along the edge, and non-linear part is missing. In hydrodynamics, it's not missing.
But then
That's a
you
bit
can
different.
look up whole papers about nonlinear effects in the gas.
In hydrodynamics, it's a rather developed story. In quantum Hall effect, H considered as a linear wave,
Yes.
which
Of
in
course,
fact
there are also small effects from the curvature of the dispersion wall.
This nonlinear effect causes various instabilities, which in hydrodynamics is well documented. I wonder whether there is an analog in Hall effect, those nonlinear effects.
So let's go for coffee.